Started. Over to you, Evan.
Thanks, Kim. Hi, everyone. My name is Evan Mutual, and I will be the presenter for this webinar. A quick blurb about myself. I completed my master's in geophysics from the University of Calgary with a specialization in time-lapse rock physics inversion. I was QI Calgary's first hire when the office was kicked off, and I am one of two technical leads here in the QI Calgary office. With that, I think I'll dive right in. And I should mention that feel free to post questions anytime that you want in the chat. I will address them at the end, but you can post the questions whenever they come up. So to begin with, just a broad overview of what we're actually trying to achieve with the 4D seismic problem. What we're trying to do is take multiple acquisitions over the same reservoir field so that we can look at the differences in the seismic amplitudes before and after production has taken place. And what we're looking at here is various different ways of visualizing the 4D seismic data. So on the top left, we have 4D seismic differences. So this is just simply taking amplitude of baseline and the amplitude of the monitor and differencing the two and looking at what the amplitude changes are. Bottom left, we have 4D time shifts. So these are representative of the change in velocity that occur, which causes a change in travel time between baseline and monitor due to production effects. And then on the right-hand side, we have a visualization of the 4D differences as a horizon. And the goal of our 4D seismic inversion process is to combine all of these different data sets together to create outputs that are more directly interpretable, have less ambiguity and noise in them, and ultimately result in products that hopefully are more directly representative of changes in reservoir properties. So here's what the ins and outs look like for our 4D workflow, going from the top where we have our input seismic AVO data sets, whether those are angle gathers or angle stacks, to the very end where we have hopefully calibrated 4D rock physics inversion results. And the process basically is that we perform a 4D-AVO inversion to extract changes in elastic properties, and then do a subsequent rock physics inversion using a calibrated rock physics model to directly estimate changes in rock properties such as saturation, effective stress, and pressure. So a visual look at what this process looks like is, once again, this is the same seismic differences on the right-hand side. As part of the initial step, we do a lot of preconditioning. So the goal with the preconditioning is to make the baseline and monitor data sets as similar as possible while maintaining the differences that are in the data sets just due to production-related effects. So a key component of this that we're going to touch on through this presentation is aligning the two data sets, but there's a lot of other preconditioning steps that can be involved at this stage, such as spectral balancing, spectral matching between the data sets, just to make sure that our wavelets are the same in the baselines and the monitor. Once we have done that, then we can perform our 4D simultaneous AVO inversion. And what we're looking at here is change in acoustic impedance. Because we're looking at simultaneous AVO inversion, this allows us to gain the extra dimensionality of looking at the shear term. So this is an example of change in VPVS ratio. And the two of these together is what allows us to, using rock physics relationships, allows us to be able to differentiate between changes in saturation, effective stress, and porosity. And we require that extra dimension to be able to separate between these two distinct production effects. So next, using our rock physics model that we've built for the reservoir, we can perform a subsequent rock physics inversion using the elastic changes in elastic properties that we've calculated. And this rock physics inversion will produce changes in elastic or changes in rock properties, as well as, importantly, 3D baseline properties. So the in situ properties of, for instance, water saturation, porosity, and volume of clay. The goal with which is that ultimately we can use these products to update our actual reservoir model. And one thing to mention, just in terms of the workflow that we use, is that it is a very iterative workflow. So what I've just shown kind of describes things in a very linear fashion, going from the inputs to the outputs. But because all of these things are so interrelated, it's very important to note that a properly conditioned AVO inversion workflow requires a lot of testing, and it isn't as simple as going from one step to another as this seems to indicate. And in particular, what QI likes to do is that we like to use the inversion itself as a framework for validating any of the inputs that are going into the inversion. So what I mean by that is that when we perform any kind of data conditioning step, whether that's an alignment or a amplitude balancing or a spectral matching, all of those steps are taken through the inversion phase to actually test what the impact is on the inversion itself, which is ultimately what we're trying to do, is get a better tie between our inversion results and our observed elastic well logs. And then in terms of the 4D-AVO inversion specifically, some, I guess, buzzwords to mention with respect to the 4D-AVO inversion framework is that it is a fully simultaneous AVO inversion that directly inverts different vintages and different angle stacks of those vintages for changes in reservoir properties and the baseline properties. So rather than taking the monitor, inverting that, and taking the baseline and subtracting the two, we invert them both at the same time, and we can do that with an arbitrary number of vintages, angle stacks, or even azimuthal angle stacks to invert directly for changes. And what this allows us to do is it allows us to keep the allow for one extra step of noise removal, in that the changes that we see have to have some kind of compliant AVO type behavior. And doing this allows for a little bit of extra noise rejection, as opposed to if we were to just invert each vintage separately and subtract the two. So I'll have two examples to show today. Both are offshore examples. One is from the South Arne field in Denmark, right near our home office. And the other is the Siba and Okum field off West Coast Africa. And we're going to begin with the South Arne field. So as a brief introduction to the field itself and the reservoir, there were 4 seismic vintages that were available for this time-lapse study. The baseline was acquired pre-production in 1995, and then 3 monitors, the first in 2005, then 2011, and an OBS survey acquired in 2014. As you can see, the production history is such that the first production was taking place in 1999, so 4 days just before the baseline, and then the first monitor was acquired 6 years after first production. And a little bit of background on the geology is that the field in question is actually quite complex, in that is a chalk field with up to very, very high porosities. You can see 45% porosity in some of the very strong buggy porosity fields. The drive mechanism is depletion and compaction and subsequent water injection. And something to note that they had to spend a lot of time on with the rock physics modeling is that in this chalk field, the chalk itself is reactive with the water. So the water causes it to partially dissolve and has a very strong impact on the rock physics. So as a result of that, there is a significant amount of compaction that takes place, and that all had to be accounted for in the rock physics model. And the goal of this study is to be able to identify areas where, first of all, identify areas where production had taken place, and secondly, use that to identify areas where we could potentially do a little bit of infill drilling to where marginal reserves are still existing. So to begin with, one key step for any time-lapse study that I'm going to demonstrate briefly with these next few slides is seismic warping or alignment. So what happens between different vintages of seismic data is that as we have production effects which change the elastic properties of the rock, this causes changes in the velocities that the seismic data actually observes. And as a result of that, we actually have observable changes in travel time between baseline and monitor surveys. So prior to us going through the process of being able to directly extract information about the changes in amplitude between a baseline and monitor, we have to correct for that travel time difference. So the first step is to align the monitor surveys to the baseline, such that when we actually are looking at the differences in the amplitude, we're looking at the differences that are due to production only, and not differences due to production and differences in travel time. So our alignment is performed in actually 3 dimensions: inline, crossline, and two-way time. And the reason why it's performed in 3 dimensions is the first 2 account for, basically, we calculate the geologic dip between each vintage and try to align the dip. And so this accounts for potential imaging issues or differences that might have occurred due to the velocities changing. And typically the orders of magnitude of these inline and crossline corrections is very small. But what it allows us to do is to produce a more robust alignment, and also allows us to produce a 2-way time travel field that is specifically only differences due to travel time and not due to imaging differences placement. Because, and this is really important, because that 2-way time travel displacement is also very useful as an interpretation tool, and as we will see later on, as an input to an absolute 4D-AVO inversion. So this is an example of what the alignment actually looks like. So on the left-hand side, we have the original seismic traces, a baseline and a monitor trace. And you'll notice that at the base of the reservoir, we do have a strong variation in amplitude between the baseline and the monitor. However, we also see a characteristic offset between the 2 traces, and that's due to the fact that the 2-way travel time has changed because of the production effects. So when we perform our alignment, what we're trying to do is align the monitor to the baseline, and that's what you see in the middle panel, where the traces are now aligned properly, so that if we were to difference these 2 traces, now we're looking at only the differences due to amplitude and not also from the offset. So if we zoom in, this is what this looks like in a more zoomed in view. So you can see that there are 2 different competing impacts that we're trying to look at here. So one is the offset, which is the difference in travel time, which the alignment is trying to correct for. And the other is the true amplitude change, which is ultimately what we're trying to use to invert. And after the alignment on the right, you can see that that offset is no longer present. So when we compare the amplitudes directly, we know that we're no longer looking at a difference that's due to difference in travel time. And then, as I mentioned, the 2-way time shift itself can be a very valuable interpretation tool. And that's because the changes in 2-way travel time are related to changes in velocities that are occurring due to our production effects. So it is very common to use this 2-way travel time as a volume in and of itself to be able to interpret where changes are occurring. And moreover, we can use it, and I'll elaborate on this a little more in the next study. We can use this field as an input to a 4D low frequency model for a 4D absolute inversion. And the other thing that's important to note here is that this alignment is not taking place as a static value that is being calculated from, for instance, picking a baseline horizon and a monitor horizon, or comparing 2 events specifically. It's a spatially and vertically varying displacement field that's calculated by optimally matching the cross correlation between the baseline and the monitor survey. And as we can see here in the before and after, the impact of the warping on the change or the differences in seismic amplitudes is actually very, very strong. So on the left panel, we can see the difference before alignment, and on the right, we can see it after. And before alignment, we can focus on the fact that there's amplitude changes that are occurring both above and below our reservoir. So this is caused, in this case, by changes in by compaction taking place that's changing the velocity structure both above the horizon and then subsequently having misalignments below. So after alignment, what we can see is that those differences that were occurring above and below our reservoir level are all but minimized. And even at the reservoir level, we can see that the actual amplitude change that's occurring is much, much more subtle than the initial difference was suggesting. And ultimately, it's this kind of subtle amplitude that we're really trying to use to extract valuable information on what changes have occurred in the reservoir. So here's a map view of just seismic differences, and this is after warp. And we have two different reservoir intervals that are being plotted. On the left is the echofisk, and on the right is the tor. And the tor is the interval that's the lower reservoir unit where more of the water injection is taking place. I want to draw attention to one specific area. There's a lot of subtle changes that are going to be happening here, but in particular, I want to focus on this one spot that is circled in red in the echofisk, where we see that there's a very strong seismic difference that's coming through that originally was being interpreted as being evidence of water injection coming in through the echofisk, so replacement of our hydrocarbons with water. But when we actually run through the rock physics inversion, we can see that in the change in water saturation, that same anomaly actually isn't present in the echofisk, but it is present at the tor level. And the reason for this ambiguity at the amplitude phase is actually because of side lobe energy that's in the seismic. So our seismic signal is band limited. And as a result of that, even when we look at aligned differences, if I go back to our plot here, we can see that on either side of our expected amplitude change, we have a strong side lobe energy. And that side lobe energy can make interpreting where the actual change is occurring very difficult, which is what's occurring here. After we go through the process of rock physics inversion, where we're constraining our solution to only expected changes that are allowed within our rock physics model, we can see that a lot of that side lobe noise is actually being significantly reduced or eliminated, which is allowing us to make the interpretation that actually that amplitude change that we're seeing was actually side lobe energy from the very significant change that was occurring at the tor level. And as a result, if we compare the reservoir models before our inversion, so using only the 4D seismic differences, again, noting that red spot where we're modeling that there should be a significant increase in water saturation. After incorporating the water saturation, change in water saturation volumes, we can see that there are a lot of changes that are occurring, but in particular, we will note that strong anomaly that's located in the echofisk is now no longer being modeled. And that was actually validated by well results where they did an infill well drill and subsequently drilled in the echofisk to try to actually extract more hydrocarbon from that interval. Next, I'm going to show an example of the Okum-Siba field. So this is West Coast Africa, and this was a very, very nice seismic data set, part of a large complex of turbidite, deep water turbidite sequence, and some brief history on the seismic data and the reservoir in question. So we had a baseline survey that was acquired in 2003, and two monitors that were available in 2010 and 2014. In this case, we can see that first production actually took place in 2008. So keep that in mind that more of our production is expected to be observable in the second monitor, which was in 2014, where the first monitor was only 2 years after first production. And as I mentioned, this is a deep water turbidite, very, very strong porous porosities in these reservoirs. And as a result of that, the expectation here was that we would potentially see a lot of effective stress change. So the porosity was being maintained by the pressure that's in the reservoir. So the expectation is that due to depleting, we would expect that we would have significantly lower pressures in some areas, and other areas where we're injecting water, maybe we would be getting overpressure. Here's an example of the 3D-AVO inversion results that are also a part of the 4D-AVO inversion. So the 4D-AVO inversion produces changes in elastic properties as well as results for the baseline elastic properties. And here's an example of the results for the baseline inversion for 2003, so before any production. And we have plots here for acoustic impedance, VPVS and density, and the inversion result is in blue, and the well log data is in red. And you can notice that for all three parameters, but particularly for the acoustic impedance and the VPVS ratio, we have a very strong well tie between the elastic property from the inversion result and the elastic properties observed in the well, particularly for the low VPVS sands, which is our reservoirs. And now the other component of the inversion, which is the change in elastic properties, what we have here is a fairly complex panel. So what we're focusing on here is the 4D change in acoustic impedance, which is one dimension of our AVO inversion. On the left-hand side, you can see the change in velocity. So this is calculated by differentiating our time shift field. To the right of that, you can see that we have a resulting low frequency model for a change in acoustic impedance. And the logic here is that acoustic impedance is made up of velocity and density. And since we have results for change in velocity and don't expect large changes in density, or if we do, we at least expect them to be the same sign or same direction as the change in velocity, we can use it directly as an input to a 4D change in acoustic impedance low frequency model. And what that looks like is in the middle panel on the left, you'll see a relative change in acoustic impedance. Relative in this case means that there is no bias. The low frequency model at this the low frequency model for a relative 4D-AVO inversion is biased to a value of 1. So 1 indicates no change. In our case, the inversion is parameterized such that the outputs are ratios of change. So a value of 1.1 indicates an increase in 10% of your acoustic impedance, whereas a value of 0.9 indicates a decrease of 10%, and a value of 1 indicates no change. So a relative inversion starts with a model of no change, whereas our absolute inversion, which is the panel just to the right of that, includes the low frequency model, the acoustic impedance low frequency model as the starting model. And you can see in the results of the absolute acoustic impedance that a lot of those side lobe energies are actually dramatically reduced, and we're able to more properly characterize the actual change that's occurring at the reservoir level. We can do the same thing looking at the 4D VPVS results. And the 4D VPVS is very important because, as I mentioned, this is what's really allowing us to potentially be able to differentiate between and decouple various production-related effects. So if we only have the acoustic impedance portion of our result, we actually only have kind of half of the solution. Various production effects can look exactly the same when looking at acoustic impedance. So we need this other dimension so that we can look at our rock physics and be able to potentially better separate between different effects. So once again, on the left side, we see the change in velocities. These have now been changed into a change in VPVS low frequency model. And the way that this is done is by calculating a cross correlation between the relative change in VPVS and the relative change in acoustic impedance. And where that cross correlation is 1, we keep the change, the low frequency model in the same state. And where the cross correlation is -1, we flip the sign and scale it by the actual value itself. So other methods, depending on if you have 3 component data, you could actually directly calculate this change in this low frequency model for change in VPVS ratio by having calculated time shifts for both PP and for PS data. But in the absence of that data, we need to do something else to be able to find a change in VPVS low frequency model, which was what was done here. And again, if you compare the relative change in VPVS to the absolute change in VPVS, you'll note that much of the side lobe energy on either side of the real response is being minimized. And we are also able to better resolve the actual extent of our changes. And now to touch a little bit more on 4D rock physics or rock physics in general. So I've mentioned rock physics a few times, and what rock physics is the study that allows us to bridge the gap between reservoir properties and elastic properties. And what we do for this is to create an actual rock physics model that describes how elastic properties change as reservoir properties vary. So reservoir properties are, for instance, porosities, fluid saturations, mineral fractions, or stress. And elastic properties are, for instance, AI, VPVS, and density, basically the quantities that we get out of our elastic inversion. So our rock physics model allows us to bridge the gap between those two and allows us to explain how the elastic properties are varying because of the reservoir properties. Some uses of the 4D rock physics model is we can use it as a forward model. So this allows us to do, for instance, scenario modeling. So what is the expected elastic response if we change our fluid and replace our hydrocarbon with water? What's the response if we deplete our reservoir by 1,000 psi or increase the reservoir pressure by 1,000 psi? But more importantly for us, the rock physics model also allows us to perform a subsequent rock physics inversion where we invert the elastic properties that are output from our AVO inversion into a subsequent inversion to extract reservoir properties. So this results in change in water saturation, change in effective stress, and potentially change in, for instance, porosity. So here's what our rock physics model actually looks like mathematically on the top. You'll see that it looks a lot like basically a harmonic mean. And when we're building the rock physics model, what we're trying to do is extract essentially the MI, which is the ith mineral, the mineral end member value of each mineral in bulk in shear modulus space. So for the instance, in this case, we are looking to extract the mineral end member properties for clay and for sand. And then there's also this M naught, which is a regression function. And just looking at this equation gives the appearance that this M naught is very, very simple and just scalar. And while it can be a scalar, more typically what it actually is has some kind of functional dependence on rock properties. So it can have a functional dependence on, for instance, stress, porosity, or volume of clay. And what this M naught actually controls physically is where the data sits between the Voigt and Roos bounds. And the reason why very often it needs to have a functional dependence on rock properties is basically that depending on what your mineralogy or your porosity is, you can sit in a different space in Voigt and Roos bounds. So essentially it allows for different compaction trends and different stress states depending on porosity and mineral. So here's an example of what rock physics model looks like. So this is the in situ case for this Okuma study. On the left side, we can see our observed elastic properties. So these are the elastic properties from the well logs, color-coded by porosity, saturation, and volume of clay. And on the right-hand side, we can see the same results if we take those petrophysical values and then forward model using our rock physics model what the elastic properties look like. And you can see that comparing these two models, we can see that we're not able to completely capture the scatter that's in the data, but certainly the general trends and the place in elastic space where each of those different petrophysical quantities are occupying is very well preserved. Once we have that model, we can now do some scenario modeling. So what this is showing is now trying to demonstrate what kind of elastic property changes we can expect if we either change our fluid saturations or change our pressures. And doing this for three different porosity states. So we have 15% porosity, 25% porosity, and 35% porosity. And what we're seeing is color coding by water saturation. So starting in the middle, where we're assuming no change in pressure, we can see that if we change our water saturation from 0, so full hydrocarbon filled, to pure water filled, we would expect there to be an increase in VPVS and an increase in acoustic impedance. And if we're looking at pressure change, what we can see is if we have 1,000 psi depletion, we would expect there to be an increase in acoustic impedance, but a decrease in VPVS. Whereas if we have 1,000 psi overpressure, we expect a decrease in acoustic impedance with an increase in VPVS. So you can see how having those two dimensions allows us to potentially separate between the fluid effects and the pressure effects. And in fact, you can see this even more obviously on the plot on the right, which is showing acoustic impedance versus shear impedance. And here what you can see is for changes in water saturation, by and large, all the change that's occurring is on the x-axis. So all pretty much in the VP, and the reason for that is that the fluid don't have shear modulus. So if we change our fluid from an oil to a water, we don't expect there to be a significant amount of change in shear impedance. However, if we change our pressure, we can see that there is both an acoustic impedance impact and a shear impedance impact. So it's those two dimensions that allow us to separate between these two different fluid effects. Here's a plot of some validation of what our 4D results look like. So we have the in situ porosity, volume of clay, and water saturation. These are plotted against our actual inversion results, and you can see that for the main sand bodies, there's a very, very good correlation. And then you have the first monitor and the second monitor, and you can see that those hydrocarbon saturated sands have now been largely replaced by water. And then on this study, there was also a confusion matrix type of validation analysis that was performed, where they tried to see where we could actually detect hydrocarbons in true change and where we couldn't. And you can see that really what we're trying to aim for here is we get true positives or true negatives. And you can see by this pie chart that for 14 wells where the analysis was done, 10 true positives were identified with only one false positive, and one true negative was identified with two false negatives. So certainly on the positive side, we're very much able to detect with a high degree of certainty where those hydrocarbon sands actually are sitting. And then here is a plot of our actual results for change in P impedance on the top and change in S impedance on the bottom for our two different vintages. So on the left is 2003 to 2010, and on the right, where more production had now taken place, we see 2003 to 2014. And in the P impedance, we can see that there's a significant anomaly that's occurring at the top, where we have gas coming out of solution. Very, very strong anomaly there that you can see is very, very not very well resolved or not very impacted on the shear impedance. And again, that's because the gas coming out of solution has a very, very strong impact on our P wave velocities, but certainly less so on our shear impedance. So we can see the hint of a little bit of hardening that's occurring in the shear impedance, but not nearly to the extent that's observed in the P impedance. So that's allowing us to be able to say with confidence that that anomaly in the P impedance is caused by a fluid effect and probably not a strong change in pressure. Conversely, where we have this arrow at the base of this well, we have an area where there's minimal change in P impedance, but a very, very strong change in S impedance. And what that is telling us, based on the rock physics relationships that we were just looking at, is that this is probably a change due to a change in effective stress. And in fact, that this is probably a change due to overpressuring. So with that, they were able to update their reservoir model. This is an example of what the client's reservoir model looked like before the inversion. So these were the expected changes in acoustic impedance and shear impedance. And we can see in particular that at that target where there's an arrow there, they weren't expecting there to be any change due to effective stress. But after having received the input of our 4D-AVO inversion, they were able to see that there was in fact a very strong change in stress taking place. So they updated their reservoir model such that that is now reflected in their S impedance. And what that looks like in reservoir properties is on the top left, we have the net to gross model. So basically where we have our sands. On the right hand upper right, we have change in water saturation. So this is where we're actually performing our injection. And you'll notice that in the bottom left model where we have the change in pressure from the model, we have a very strong correlation now between our change in pressure from the model versus the change in pressure that we're observing in the data, which is on the bottom right. So you can see how we use those inversion results, or the client, sorry, use those inversion results to update their reservoir model such that it now matches the seismic data. So kind of closing the loop. And finally, here's an example of what the water saturation results look like through a horizontal well bore. So on the left-hand side, we can see a horizontal well bore that was drilled into two distinct anomalies, and we can see that there's hydrocarbon that's been identified in the rock physics inversion in those two different bodies. And on the right-hand side, we can see that for the most part, those two lobes have been completely drained and are now saturated with water after injection. But at the toe of the well, we can see that there actually is some remaining hydrocarbon, and that was also confirmed by a monitor of the well, and we could see that we were able to properly capture where that reservoir wasn't actually drained. So now to, I guess, go over the highlights of what 4D seismic inversion actually offers. Is it allows us to go from reflectivity and just amplitudes to actual reservoir properties. And not only does it allow us to go from amplitudes to reservoir properties, but it actually allows us to also, in the process, allows us to remove a lot of the ambiguity, for instance, side lobes or time shifts that are present in the data prior to going through the inversion process. So we get outputs that are more directly interpretable across disciplines, and we also get outputs that are more robust as far as identifying where changes are actually taking place. Through the process of the 4D-AVO inversion, we combine changes in amplitudes and the time shifts. So we use the time shifts that we create in the alignment process in the building of the 4D low frequency model, and then we combine the two together in an absolute 4D-AVO inversion to get the best quality inversion result. So it's integrating various different data sets together to get one output. And as I mentioned, it allows us to integrate geophysics and geology such that the quantities that we're actually getting as outputs, rather than just being purely geophysical type terms, are stuff that can directly be used as in inputs in reservoir modeling and for reservoir engineers. And this allows us, and the process allows us to condense massive amounts of seismic data in just a few reservoir properties. So as an example, for a given project, we can have 100 different volumes where we have 4 different vintages, 5 angle stacks with 5 different azimuths, 80 well logs with, or 10 wells with 8 well logs each. And then all of that results in 5 fully calibrated volumes where we have the initial porosity, initial saturation, initial volume of shale, and then 3 changes in oil saturation. So all of this data getting condensed into a smaller amount of final products that are more directly usable. If anyone wants to look in more detail at any of the 2 studies that I'd shown, they have actually have publications attached to them. So be sure to check out our website. We have a publications blog